Okay, hello everybody. Uh, I was really looking forward to come to this meeting, which celebrates a very dear friend who has, in many ways, tremendously influenced both my professional as well as my personal life. I'm sorry I could not do that. So here is a poor electronic substitute for that, and I hope it works without a snag. 36 years ago, I landed at the University of Chicago as a fresh graduate student, and I soon met an intense young man who was passionate about everything from physics to classical music to painting and, of course, politics. That was Spenta. And at that time, he looked sort of like this. So let me try to share the screen. Can you see this?
Yeah, we can see it.
Okay, so this is what it looked like. Now, nowadays, of course, he looks very distinguished, but if you look very closely, his intensity has not diminished. However, I did catch him once going fishing. I actually forget where this was. So anyway, Spenta introduced me to the exciting world of quantum field theory. And he infected me with a passion to understand. We had very long sessions in a small room, which was the annex of the library of Enrico Fermi Institute. That building doesn't exist anymore. And those sessions provided me with my first physics toolkit, and to a large extent, it shaped my taste, not just in physics, but in music, art, literature, and whatnot. In return, I could only introduce him to Bob Dylan and to Chicago blues in a club called the Checkerboard Lounge. So soon Spenta joined TIFR, and I went on to Fermilab and then to Caltech. And it was Spenta who urged me to apply to TIFR. Now, I have been to TIFR before, and I thought, getting a job there was really a long shot, but I did it anyway, and somehow it worked. And then Spenta convinced Ashok to come along as well. So in 1987, I came to Bombay, and by that time, Spenta and Sunil had pushed India into the world of string theory. Very soon, Avinash joined, and then Ashok came, and then Gautam, and then Sandeep, and then Atish, and then Shiraj. None of this would have happened if not for Spenta's initiative, his commitment, his leadership, and in belief in, yes, we can. We all know of Spenta's landmark contributions to quantum field theory and string theory over the years. What many of you may not know is the breadth of his scientific vision. This is, of course, reflected in the way he built ICTS as a center for theoretical sciences and not just theoretical physics. I really appreciate that. So, Spenta, happy birthday. We all look forward to many more years of superb physics from you and many more years of leadership in shaping science in India. So I have what, like 20 minutes left?
Yeah, 20 plus 5.
Okay. So I will talk about, I give a kind of a brief survey of something which I have been working on for the past 3 years or so. And this deals with some specific properties of quantum quench. I've collaborated with Damian Galante and Robert Myers, Dittarka Das, Krishnendu Sengupta, and more recently with Pavel Kaputa and Masahiro Nozaki. Let me do this. So, as we all know, an efficient way to produce excited states in quantum many-body systems is to subject it to a quantum quench. So typically, what one does is to start with the ground state of an initial time-independent Hamiltonian and then introduce time dependence so that at late times one gets another time independent Hamiltonian with a coupling profile which looks like this. The Heisenberg picture state is then an excited state of the new Hamiltonian. The excited states, of course, evolves non-trivially in time, and we are typically interested in a variety of questions about the resulting non-equilibrium state. One set of questions, which I will not talk very much about, relate to thermalization. How does the system reach a steady state, and in what sense is this state approximately thermal? Another set of questions, which I'll concentrate on, relates to universal properties of various quantities for situations when the quench involves the vicinity of critical points. These are questions which involve sometimes early time behavior in the critical region. An important aspect of this is a scaling of expectation values with the quench rate and the exponents being determined by the critical point. So what I'll do in this talk, I will explore some very well-known as well as some newly discovered scaling properties in continuum quantum field theory as well as in lattice theories. And I'll also, if I get the time, I'll also discuss some recent work on possible scalings of the entanglement entropy, again with the quench rate. So the kind of quantum quench we will talk about involves an action which is a deformation of a critical action with a relevant operator with a coupling which is time dependent and has a time scale delta t and an overall amplitude which is lambda naught. So this function lambda of t is chosen such that it goes through a zero, and going through a zero means that it goes to what would have been an equilibrium critical point, as typically as some power of t. In fact, the generic situation would have r equal to 1, so it would go linearly in t near the critical point. When the quench is slow compared to the physical mass scales in the problem, Kibble and Zurek, long time ago, proposed that, of course, as the initial evolution of the system is adiabatic, since the quench is slow, but of course, since it is approaching a critical point, at some point, the adiabatic evolution breaks down. This is called the Kibble-Zurek time. And they assumed, to a first approximation, that as soon as this happens, that means the adiabatic evolution breaks down, the system becomes diabatic and gets frozen in the state at that time. You also assume typically that the instantaneous correlation length at this time is the only length scale in the critical region, and they can be easily determined by using standard criteria in terms of delta t, lambda naught, and the critical exponents. An improved version of this gets rid of the assumption that the system is really frozen. Rather, it involves some scaling functions, and the scaling functions involve ratios like t upon t kz, or correlation functions x minus x prime upon xi kz, where xi kz is the correlation length at the Kibble-Zurek time. Now, everybody admits that the initial assumptions of Kibble and Zurek are too simplistic. Nevertheless, the scaling results hold for many models. Of course, Kibble-Zurek was originally proposed for thermal transitions at non-zero temperatures, and there is some experimental evidence for this. For quantum transitions, there are many experiments, but it is not at all clear whether this form of scaling still holds. So over the past several years, some insight into the origin of these scaling functions have been gained by obtaining holographic realizations of this problem. In holographic realizations, a quantum quench corresponds to a time-dependent boundary condition for a bulk field, which is dual to the boundary theory operator which is being put in. And in several examples, the scaling behavior arises due to the dominance of a zero mode of the dual bulk field, and when the system crosses a critical point. Once that happens, the bulk equations of motion simplify and the scaling form of these functions follow. Bushell, Leonard, Myers, and Van Niekerk looked at the opposite regime of this using this holographic setup. So instead of looking at slow quench, where delta t, the time scale of the quench, is large compared to the inverse initial gap, they looked at the regime when delta t is small compared to the inverse of the mass gap. They found in these holographic calculations, in numerical calculations to begin with, a different kind of scaling behavior for quenches which are driven by bulk scalars. And what these scaling behaviors look like are as follows. Like at the expectation value of the operator which is being quenched scales as some power of delta t with an exponent which is entirely controlled by the dimensionality of space-time and the conformal dimension of the operator O. In a similar way, the energy, the excess energy which is produced, scales as basically the same power of delta t. These results, first obtained numerically, can actually be understood by noticing that this regime, and in this regime, the response is dominated by the space-time which is close to the boundary. It turns out that this result, which looks too good to be true, is in fact a result in any relativistic quantum field theory, regardless of holography. The proof is in fact so simple that I thought I'll just run through it. So what we are considering is a deformation of a conformal field theory by this operator. And again, there is this coupling which is time dependent, which is of this form. We are going to take this time dependence to be quite general, except that it's going to start at some time t equal to 0. It can do excursions above and below the initial value lambda naught, and then again becomes another constant after some typical time scale, which is delta t. So given this, let us start calculating this expectation value of the operator in standard perturbation theory. And I've written down the first few terms of the difference of the expectation value from the expectation value in the initial value of the coupling. The quantities which appear here are retarded Green's functions and three-point functions. And I should emphasize that all these quantities are in fact renormalized quantities. It turns out that it requires counter terms which depend on the coupling as well as its time derivatives. And these counter terms can be read off with precise coefficients from adiabatic expansions. So let's consider the first term. It's an integral over space and time of this retarded Green's function together with this function which describes the time dependence. The integral over time, because this is a retarded function, of course, goes from 0 to the time of measurement, which I call t. The integral over x is in principle has been written over entire space, but the Green's function is a causal Green function. So that means that only the region inside the light cone of the point at time t has a non-trivial contribution. So now let us suppose we want to calculate the quantity at t equal to delta t, basically right at the end of the quench. So what this means is that both the space and the time intervals which appear in the integral are at most of size delta t. So recall that the scale delta t is much smaller than all other physical scales in the problem. So what this means is that, and since all the arguments of the Green's function are also of the at most of the order of delta t, so what this means is that the Green's function, which is actually the Green's function of the initial theory, is basically the conformal field theory Green's function. In turn, that implies that this leading contribution, the only scale which appears in the integral is in fact delta t. The rest is in fact dimensional analysis, as you might suspect. This quantity has an expansion in terms of a dimensionless coupling, which I have defined as G in here. In the fast quench limit, by definition, it is this dimensional coupling which is small, and therefore the leading term just gives the answer which I have just advertised earlier. So there's a similar argument for the energy density and some other operators, and in particular for the energy density in our setup. Once we know what the answer is at t equal to delta t, we also know what the answer is at late times, because the Hamiltonian basically becomes constant after that. I would like to emphasize that this result depends only on the properties of the conformal field theory in the UV. And if you want to have a more detailed understanding of the general results, there's this paper of Berenstein and Miller, which does a good job in elucidating many of the points. And of course, most of the explicit calculations which explore various aspects of this which we have performed appear in solvable free field models. At the very other extreme, universal behavior is also known for instantaneous quench from a gapped phase to a critical point. Most famously, the work of Calabrese and Cardy, who argued that the quench state obtained as a result can be approximated by a state which is related to a boundary state of the final conformal field theory. And in 1+1 dimensions, using the technology of boundary conformal field theories, this leads to many interesting results at late times. For example, the relaxation times for various expectation values of various operators, the ratios of them are universal quantities determined by the ratios of the conformal dimensions. There are subtleties with this, which Gautam and his collaborators have looked at, and I refer to their paper for that. Now, it may appear puzzling that the formula which I have written for the expectation value of the operator actually diverges in the limit in the case when the conformal dimension delta is greater than d upon 2. On the other hand, this should be the abrupt quench limit. The reason, of course, is that we have been considering renormalized quantities. So the quench rate is fast compared to the physical mass scales, but slow compared to the ultraviolet scale. So in order to understand this better, what we would now like to do is to study this issue in solvable models, focusing first on ultraviolet finite quantities, but still staying in the continuum. So one interesting ultraviolet finite quantity is, in fact, the excess energy. So here is the kind of free fields for which we would look at, like a free scalar field in some arbitrary number of dimensions with a time-dependent mass or a fermion. And the idea is to look for profiles of these functions, mass profiles, such that the equations of the quantum equations of motions can be solved explicitly in terms of known special functions, which are typically hypergeometric functions in these cases. And the rest of the work is to do some integrals in momentum space, which of course we do numerically. So here is one example of an ultraviolet finite quantity, which is the excess energy. This is the energy at late times subtracted by what would be the ground state energy at the final value of the coupling. This quantity is ultraviolet finite for any finite delta t, since the additional counterterms needed to render this quantity involve time derivatives of m squared, and these all go to 0 at late times. And I've shown here a table of the answer for this kind of quantity in various dimensions for scalar field theories. And what you would notice in here is that for low dimensions, this quantity indeed has a finite limit. And there are corrections, and it is the leading corrections which in fact are consistent with this universal formula which I have been showing. However, at high dimensions, this quantity diverges in the limit when delta t goes to 0, and it is this leading divergence which gives that universal scaling formula. Now, these are all results in free field theories. We don't have any proof for arbitrary theories, but we do have a conjecture, and the conjecture is that there is a marked difference for response by quenching an operator whose conformal dimension is less than d upon 2 as opposed to greater than d upon 2. Namely, in the second case, the excess energy in fact diverges. Okay. Here is another interesting quantity, which is ultraviolet finite. This is the 2-point correlation function at a finite spatial separation at some given time t, equal time correlation functions. And here is a plot of this correlation function with some fixed number which is subtracted as a function of this time scale delta t, which is on a logarithmic scale. And these different colors are different values of the spatial separation. And what one finds is that when the separation is small compared to delta t, but large, when delta t is larger than the separation, but smaller than the inverse mass, then this correlator scales with delta t is exactly as like the renormalized expectation values. Whereas for delta t much smaller than r, it saturates as a function of delta t as one would expect. So far, our results are in continuum field theory. To explore the entire range of quench rates from abrupt quench, which is really a quench at the scale of the lattice spacing, to a slow quench, what we need to understand this is in theories with a finite lattice spacing. And this possibly would be necessary to make contact with experiments as well. So recently we have found some exactly solvable quench protocols in several solvable lattice models. And these are favorite models which people usually look at. So one of them is a Ising model with one-dimensional Ising model with a transverse field which is time dependent, and the other one is a two-dimensional model, two-space dimensional model, which is called the Kitaev honeycomb model, which has some interesting features as we'll see. The Ising model has an isolated critical point, whereas in the Kitaev model there is an extended critical region of the coupling space, and it so happens, so there are these three couplings in the Kitaev model, and wherever the three couplings can form the sides of a triangle, you have criticality. And this gives rise to several distinct classes of critical behavior which depend on relative values of the three couplings, which leading to different continuum quantum field theories. So our idea is to explore these by keeping two of these constant in time and solving the theory for a time-dependent J3 of 3. And again, the trick is to find a dependence for which you can solve this exactly. Quantum quench in these models have been studied in the past, most extensively for linear time dependencies, as well as for abrupt quenches. In these cases, it turns out that this problem can be mapped into a Landau-Zener problem, which is most easily solved when the quench starts at very early times. And the purpose here has been to explore Kibble-Zurek dynamics. We are, however, interested in profiles which asymptote to finite values at early and late times, and in which case the quench rate itself can be separated from the amplitude. Furthermore, we are also interested in the change of the scaling behavior as we pass from the extreme limit of an abrupt quench to that of the slow quench, with a possible intermediate regime which shows the new fast quench scaling. So I'll just give you a glimpse of some of the results. So by the way, the reason why these models are solvable, of course, is that they can be written in terms of fermions. So I've written some formula here. And this is one of the profiles of these couplings, typically the tan hyperbolic form, for which we can have an analytic solution in terms of our geometric functions, and then we again calculate the resulting integrals numerically. I have 1 minute 22 seconds. Okay. So here is the result for the Ising model, where you see 3 distinct regimes showing some power of showing various behavior. So the plot is, this is the response, which is typically a bilinear of that fermion, and what is plotted on the horizontal axis is the time scale delta t. The inset shows the kind of quench we have performed, and so the blue is this one and the yellow is that one. But they have the following properties. One, everything is in lattice units. So when the quench rate is very fast, comparable to the lattice scale, we see that the result, of course, becomes saturates as a function of delta t. We can calculate what should be the answer for an abrupt quench, and these results are in perfect agreement with that answer. In the regime when the quench is slow compared to the initial gap, which is in the large delta t, the straight lines in the logarithmic plot correspond to a slow quench, which is consistent with what is expected from the Kibble-Zurek scaling. But then there is this intermediate range between an abrupt quench and a slow quench, which in this case becomes log, and that is the answer which comes from this continuum theory which I have mentioned before. In the Kitaev model, the variety of critical behaviors give rise to various kinds of scaling, and this table just gives you some idea of the kind of dispersion, critical dispersion relations which you get in the problem. And so we have looked at all these various things which probe these different kinds of continuum field theories. And we always find these 3 different kinds of behavior: a saturation at quench rates at ultraviolet scale, a fast quench scaling at intermediate rates, and a Kibble-Zurek behavior whenever this is appropriate. For example, this is the result which comes, which happens when you start the system in a gapped phase and make a measurement of the response at the time when it precisely enters that critical region. And these again are the 3 kinds of behavior. And just one more example is a quench which lies entirely in the gapless region. And if it is lying entirely in the gapless region, there is of course nothing like a slow quench. So everything is really like a fast quench, and indeed the results are consistent with what we expect from from our considerations. Now I think I have gone over time already. Is that right, Rajesh?
Hello? Yeah, we should wrap up if you're done.
Well, I'll then skip the stuff about entanglement, entropy, and then probably just mention, just in conclusion, that our results show there is an interesting universal behavior for quench rates at intermediate scales between the ultraviolet and the physical mass scales. And maybe this can be proved in experiments. We have mostly concentrated on the behavior near the end point of the quench. As I emphasized, while this indeed gives the late time results for conserved quantities like the energy density, it would be interesting to explore how this universality manifests in other quantities at late times. and their implications to thermalization. And in particular, the stuff which I didn't talk about, we looked at how the entanglement entropy also has some scaling relations with the quench rate. It will be interesting to see how this kind of relation appears in the time evolution of entanglement, which has so far been studied only for abrupt quenches. So I'll end my talk, thanking once again, and happy birthday, Spenta. Thank you.
Thanks, Sumit. So a quick question.
Sumit, I got confused about something in the middle of your talk, probably something stupid, but at some point you said that there were ADS-CFT results giving you giving you some scaling relations with delta t, and those results were presumably in the completely renormalized theory from the point of view of field theory.
That's right.
The UV cutoff had been taken all the way to infinity in getting those results. Right? And
That's
then
right. Yeah.
Later in your talk, I understood you saying that there were situations in which those results don't hold, but there were extra divergences with M. Did I understand?
No. Let me get back to the, yeah. So those results do hold, but if you just look at, say, one of the results, can you see the screen?
Yeah.
Yes.
Okay. So you see that the expectation value of the operator goes as delta t raised to this power d minus 2 delta.
Yes.
Okay. And this is the result from the holographic analysis as well as the result which the proof which I gave just in renormalized continuum field theory. The puzzle was that this seems to diverge when the conformal dimension is bigger than d upon 2.
And you said the divergence is cut off by the UV cutoff. Is that the point? Sorry.
No, the divergence is a physical divergence. Yeah, it is. It is a physical divergence, and so that actually becomes a little bit clear when you look at these physical quantities like the energy density which is produced. You know, these are resolved for a free field theories at various dimensions. So for d equal to 4 and greater than or equal to 5, they correspond to this delta greater than d upon 2. And then what you find for any finite delta t, if you take really the abrupt limit of this quantity, you actually get a divergence. So it's okay. And the reason why, so if you actually did the calculation for an abrupt quench for these theories, the claim is that you will get a divergent result.
Thank you. Sorry. Thank you.
Yeah.
Okay, thanks very much, Sumit, for joining us. It's already quite late, I guess, for you also. And so it's great you could do this. So let's thank Sumit again.
Thank you.